Hello and welcome to my presentation with the title Concept and Economic Evaluation of Prescriptive Maintenance Strategies for an Automated Condition Monitoring System. My name is Robert Meissner. I'm from the German Aerospace Center and in particular from the Institute of Maintenance, Repair and Overhaul, and we are located in Hamburg, Germany. First, let me give you a brief overview about the motivation of our study and the objectives we are trying to follow with this presentation. The International Air Transport Association is estimating a cost-saving potential within the aircraft MRO industry to be about 3 billion euros annually, and they are stating further that this is mainly achieved through the implementation of digitalization technologies and the subsequent avoidance of operational interruptions. Additionally, there's quite an extensive body of literature in the field of remaining useful life prediction, and many of these publications are trying to timely detect upcoming system faults and somehow allow a projection of component failures. Furthermore, there's quite a variety of publications that try to quantify the effects of PHM technologies on aircraft maintenance operations. However, many of these publications insufficiently consider different maturity levels of the underlying PHM technology. Additionally, several studies show that companies are hoping for substantial smoothing of their operations through post-prognostic maintenance, but they are hesitant to adopt it. And a lot of this hesitancy comes from the lack of the identification of viable business case scenarios. And this is mainly due to low technological maturity levels of the underlying PHM technology. And this lack of a viable business case scenario results in a low willingness to further invest and ultimately leading to a slow progression of technology improvements. We are trying to follow on three objectives for this presentation. First, we would like to introduce a so-called holistic approach by considering multiple maintenance-related stakeholders and their individual objectives and needs to identify most suitable maintenance downtimes with minimal adversarial applications for each individual stakeholder. Then we want to utilize established metrics in the field of PHM technology evaluation, so to ensure a swift integration of various PHM technologies and their respective capabilities, a quick estimation of the subsequent effect for the technology expert. And last but not least, to increase the confidence in the viability of our simulation results, we want to calculate different performance indicators that strongly adhere to real life parameters that are used by practitioners and that enable a more complete representation of the expected implications by adopting such a prognostic-based maintenance strategy. Let me quickly introduce you to some theoretical concepts for our presentation here. First of all, I want to give you a brief overview about the history of condition-based maintenance strategies. You can see the level of complexity that is increasing from left to right, and the generated benefit with each maintenance strategy is increasing from bottom to top. If we're starting on the furthest of the left, we can see the maintenance strategy of descriptive maintenance. And this maintenance strategy is basically a pure retrospective analysis of and gathering of historical failure information, and also trying to identify what subsequent maintenance tasks have been issued once such a failure has occurred and has been identified. If we want to extend this knowledge and have more in-depth insights into the current state of our system, then we would shift the focus to diagnostic maintenance. And there we're trying to answer the key question of why did the specific failure happen? And there we are trying to identify a failure root cause analysis and the subsequent effects such a failure has had on aircraft operations. Coming to the third step, which is arguably the most discussed right now, is called predictive maintenance, and there we extend our insight of the current state of the assets towards the future, and trying to predict future behavior However, predictive maintenance is still asset-centric, meaning that we are focusing on purely the asset itself and neglecting surrounding areas, and trying to analyze historical data combined with real-time measurements and trying to identify what the future behavior and future degradation of such an equipment would be. And if we're trying not to answer only when a specific asset is going to fail, but what maintenance measures I shall take, then we are talking about prescriptive maintenance. And there we are extending our view beyond the asset itself. And the asset could be the aircraft, could be an engine, could be a tire. And we're trying to derive the most suitable maintenance opportunity by considering adjacent processes and the state of the involved stakeholders. For some of you, prescriptive maintenance might be a new phrase, so let me give you a brief definition that we at least agree in our institute on. And we define prescriptive maintenance to utilize a system's failure projection to minimize the adversarial implications for the involved stakeholders by an optimized proactive scheduling of necessary maintenance restoration tasks. And as I've shown you, it is an evolution of predictive maintenance, which for us solely focuses upcoming system failures and doesn't include any surrounding processes. And therefore, prescriptive maintenance, because it does include these surrounded processes, it allows a more holistic analysis and optimization of maintenance measures. Let me highlight a few aspects I see as important in this definition. And first of all, we are talking about a failure projection because we are talking about an evolution of predictive maintenance. And this failure projection is necessary to determine the suitable maintenance opportunities and also identify when ultimately our system is going to fail and try to connect the corresponding tasks to each maintenance opportunity. Then I highlighted here the adversarial implication that is indicating that we are not just focusing on the pure monetary metric consideration, but we are trying to extend our matrices towards aspects such as ecological impacts or societal impacts. However, with societal impacts, we mean the impacts right now on people that are working within the MRO industry and not people outside of the MRO industry. Then we are trying to shift the focus from the asset itself towards individual stakeholders' needs, because ultimately these stakeholders need to be convinced about the viability of the underlying business case scenario and need to be convinced that spending further on the development of such PHM technologies will ultimately yield any benefit from them. And last but not least, I mentioned it earlier already, the holistic analysis. We understand holistic analysis by not just focusing on aircraft maintenance operations, but also trying to incorporate different aspects of daily airline routines, such as the airline operation itself, but also subsidiary services such as supply chain management. Now let's talk about the use case scenario that we have examined with our work here. We had two research questions, one main one and one sub-question. The main one was, how does the maintenance performance change with the introduction of a prognostic-based maintenance strategy? And also, how does it change for different prognostic horizon? And the prognostic horizon for us is an indicator for the technological maturity of the underlying system. And secondly, the sub-question was, what are the effects if the maintenance stations operating hours are reduced from 24 hours to 16 hours or 8 hours respectively? What it means, we will see later. First, let me come to some key features of our analysis. For this analysis, we have used a Python-based discrete event simulation framework. This framework is called PREMATE. PREMATE stands for Prescriptive Maintenance Developer. And this framework simulates the interaction between airline operations and on-wing aircraft maintenance. At least in this use case, it does. In reality, PREMATE is capable of extending the interactions and also considering some sort of supply chain management. Then we have simulated an aircraft fleet that consists of 5 A320 aircraft. And these A320 aircraft have been scheduled to follow a representative pre-pandemic flight schedule from a major German airline. And we also modeled some limitations of availability of ground resources. And these ground resources were mainly available qualified mechanics. And we also limited the available maintenance hub that can be taken and chosen from for the maintenance task execution. Then, as I mentioned earlier, we varied the prognostic horizon of the underlying PHM technology, and we also varied the availability of the maintenance staff, leading to this 16 or 8 hours maintenance operations at our maintenance hub. And last but not least, the main objective for our maintenance downtime scheduling was the avoidance of operational delays due to waiting times for services. Although there are quite a number of objectives, we didn't choose any monetary aspects, but wanted to stick with the objective to avoid these operational delays. Our use case scenario was the tire pressure maintenance task. And how does it look like, conventional tire pressure maintenance? Tire manufacturers required aircraft operators to perform a manual tire pressure check every third calendar day. And before a viable pressure measurement can be conducted, there needs to be an extended cool down time of at least 3 hours after landing before such a pressure measurement task can take place. Then the tire pressure maintenance task is a pure condition-based maintenance task. Besides these hard time interval pressure measurement, we are having maintenance tasks issued solely on the wet tire pressure. And there's quite a variety of these restorative maintenance tasks, and they can range from simple repressurization tasks up to, for deeply underinflated tires, up to a tire replacement. And a tire replacement by nature results in extended maintenance downtimes and excessive material costs. And last but not least, because the recorded pressure values do not need to be stored, at least not from a regulatory standpoint, it is hardly possible to enable some long-term trend monitoring of the pressure degradation of the aircraft. Let me quickly come to the underlying scheduling method that we have applied. So here we can see a timeline, and let's just assume a certain portion of the day is blocked for non-operating hours at our home base. So no aircraft is allowed to land or take off in this specific time frame. Excuse me. And here we have 2 aircraft that are following a certain flight schedule. And first, we are looking into a predictive maintenance scheduling. And as I said, the aircraft are following our flight schedules, having some inbound flights to our designated maintenance base and some outbound flights to some random outside stations. And incidentally, both aircraft will require restorative maintenance tasks at the same time. However, I have a limitation of my maintenance resources to just 1 aircraft that can be served at the same time. And therefore, if I choose aircraft 1 to be served, the second aircraft needs to wait for its service to complete. And while the first aircraft has been served, it can commence its outbound flight right before the beginning of the non-operating hours. And right at this point, the second aircraft can start to be served with its maintenance task. However, due to the time shift now, the end of the maintenance task has been shifted well within the non-operating hour phase of the day, resulting in some operational delays for my second aircraft. So what does the prescriptive maintenance scheduling look like now? I have the first aircraft with an inbound flight. So basically now I'm at my designated maintenance station, and I will reschedule the maintenance task to exactly the time span and have the maintenance task completed for the first aircraft. The second aircraft will just normally continue its flight rotation plan. And once the maintenance task is completed for the first aircraft, it will go back into service and will also follow its flight rotation plan. And then I'm coming to, for the second aircraft, to the predictive system fault timestamp. And now I can see I don't have any other aircraft that needs to be served at that time. So therefore, my maintenance task can take place at the intended time slot. And this leads to the scenario that both my aircraft can commence their outbound flight right before the beginning of the non-operating hour period. So what does it look like now in the results of our study? First of all, we have plotted here the average total waiting time per aircraft over our simulation time span. The simulation time span here was 30 days. And you can see the total waiting time plotted over the prognostic horizon. And first, what we can observe is that the total waiting time is continuously decreasing for increasing prognostic capabilities. However, at least for our parameter setting, there's a saturation point at about 6 to 8 flight cycles. And after this saturation point has been passed, any addition of a prognostic horizon capability will yield a decreasing improvement of total waiting time reduction. And furthermore, what can be seen, and this is indicated by the different shapes of the little dots in here, we can see that between 16 and 24 hours maintenance operation, this is indicated by the little circle and diamond shaped dot, there's hardly any difference in the total waiting time. However, if we decrease our maintenance operations to 8 hours a day, we can see there's a significant increase of the resulting waiting time for each individual aircraft. We further have examined the maintenance cost difference compared to the conventional approach. And we can see that the maintenance cost is decreasing, and this decrease can primarily be addressed to the avoidance of costly restorative maintenance tasks, and mainly these costly maintenance tasks are tire replacement. If I measure more frequently, I will detect underinflations of my tire more frequently, and therefore I am able to avoid deeply underinflated tire on a more regular basis. However, what I also can observe that due to the little time that is needed for the completion of a manual tire pressure reading task, and therefore the little cost share that is associated with, the pure avoidance of manual tire pressure maintenance tasks is only yielding very little advantage. And therefore, it's much more important to avoid costly maintenance tasks than to reduce short maintenance tasks, such as the pressure reading task, by costly automating or building up an automated infrastructure. And furthermore, we have also examined the fleet utilization. And here I would like to get your attention on the first and the last column. And the black columns are the important ones here, as they represent the 16-hour maintenance operations. There we can see that the fleet utilization is decreasing compared to our conventional scenario. And this is due to the movement of the maintenance task to earlier time slots where it actually wouldn't be necessary at this point. And therefore, this increases the maintenance task frequency. And an increased maintenance task frequency combined with the extended cooldown time after landing basically eats up all our improvements by avoiding this competition for the limited ground resources. So what is the outlook from our studies? What we identify as next step is, first of all, there needs to be some inclusion of environmental factors. Here we have mainly focused on time and cost aspects, but as the focus from our society and our attention from politics and regulation shifts more to aspects of sustainability, we are advised to include CO2 equivalent emissions as well into the maintenance task identification here. And Also for our scenario, we assume that all our 5 aircraft are equipped at the same time with the same PHM technology. However, in reality, there would be a continuous rollout of such a technology, and therefore we need to evaluate the effect for a variation of this utilization degree. Then, of course, we need to extend the PHM performance metrics. Here we have only focused on the prognostic horizon. However, there are furthermore, such as the projection accuracy and false or missed alarm rates. And ultimately, we have talked about the holistic approach, but at this point, we only focused on the connection between operations and aircraft maintenance. And therefore, we also need to consider the effects such as on supply chain management. For the first 2 parts, I kindly refer to another publication that we have, which has been published in the Journal of Reliability, Engineering and System Safety. This is open access, so please feel free to have a look in there. This is my presentation. Thank you for your attention, and I'm looking forward for any discussion. Thank you.